Good afternoon. Today I will complete the part about dimensional reduction, and then we will continue with clustering algorithms. So last week we arrived at factor analysis. So the factor analysis is and somehow complementary to principal component analysis. In principal component analysis, we take the original data and map them into lower dimensional data, lower dimensional space, with the goal to preserve the variance of the data. In factor analysis, we go from opposite direction. So we think that the data which are d-dimensional are actually generated from some lower dimensional data from some so-called factors. Therefore, the name factor analysis. And we suppose that the data, for example, here, xi, as you can see, just to recall, xi volt means that this is one column of our observation matrix, or the observation matrix capital X, and here we have x 1 1 1 2 x 1 d-dimensional, and altogether we have capital N samples, so n1 x and d. And one column is denoted as boldface. I denotes ith column of the matrix. So the ith dimension, ith column, minus its mean mu I. So we suppose that the data, the left side is centered. It's composed of factors z1 till zk times loading, so-called loadings, which are coefficients v I sub 1 till I sub k. What is interesting, the loadings v are actually a matrix of dimension d times k, where k is the lower dimension, it's the number of factors. And of course, we suppose that the mapping is not exact, so there is some noise term, epsilon I, that this could be a difference between the combination of the factors and the real value of the attribute, ith attribute minus its mean. We require that for all the factors, the expected value is 0 and variance 1. And they are both all pairwise independent, so the covariances of any two pairs where I and Z, where I is different from J, is 0. As I said, the noise can be non-zero, so the expected value for the noise is some constant for each dimension, and we expect that the covariances of the noises are 0, so they are independent. Okay. Also, the covariances between the noise and the factors is 0. We will not cover how to compute the factor analysis. Actually, the factor analysis can be done using some similar method as for principal component analysis. We solve a different equation, but the equation can be interpreted that from the variables z, the factors, we would like to make a linear transformation into the centered data. So this capital X minus the means for each each column. And therefore the solution is also can be based on eigenvector decomposition of some metrics. But we will not cover that. For us, this will be a method function which will compute the factor analysis. So here I would like to illustrate the difference between the principal component analysis and the factor analysis. So for principal component analysis, we take the original data and compute new vectors by linear transformation, and it is denoted here. So we subtract the mean value and multiply from left by some matrix W, which will make a linear transformation into different number of dimensions. In factor analysis, we actually take some small matrix V. Here the matrix W was small. This was just a matrix containing several eigenvectors with the highest eigenvalue. For the factor analysis, we obtain also similar matrix V, which is computed in a little different way. As I said, it could be based also on eigenvectors, and we solve this equation, and from that we obtain as the solution we obtain the factors Z1 to Zk. In both cases, the transformation is actually linear. So while in factor analysis, we take some data which are almost normalized, mean 0, they are independent, and excuse me, I was fast. So mean for each factor is 0, variance is exactly 1. So these data are in all dimensions almost homogeneous, and we transform them by multiplying and rotating. So we obtain the original data. Next method is called multidimensional scaling. Multidimensional scaling has a very simple idea. If we compute distances between the observations, so xi and xj, this is i's and j's row of the observation matrix, so two observations, and we can compute difference between them in some norm. So it's denoted here with double vertical lines. So norm of the difference between two observations is denoted as the ij star. And this is the difference between pairs of observations. And we would like to map the observations in some other space, and in the other space we would like to preserve the distances. So there is some function which, based on some parameters theta, and the input vector x, it computes the new vector z. This is the transformation. In classical multidimensional scaling is called sometimes metric multidimensional scaling. This transformation is actually linear transformation. So we need some matrix W, and we multiply W times the vector X, and in this way we obtain the new vector Z. This is very similar what we did in PCA, for example. But in general, if we would like to preserve the distances, we can lose the or relax the requirements of linear mapping. We can use any mapping, and then we can instead of linear transformation, we can decide to minimize so-called Semon stress. And let us look at this formula. So the this formula here, we have the distance in the original space, distance between pair of observations I and j. This is the distance between the mapped versions of these two observations. The difference between these two distances is squared and normalized, divided by the original distance in the original space, and we sum all these differences, so differences in the distances in the original space and distances in the second space in which we map the data. And so here we sum through all pairs I and j where j is greater than I. So we sum such normalized square differences between these distances over all pairs of observations. And then we normalize that by dividing by sum of all distances of all pairs in the original space. And our goal is to minimize this, because if we minimize this, this means that we minimize the distances, also differences of the distance in original space and distance in the second space in the map of the map observations. It looks like much harder problem. However, we can use any optimization method, for example, some form of gradient descent method, to optimize this function, to look for minimum of this function depending based on arbitrary mapping value for arbitrary mapping for this vectors z. And this is implemented in scikit-learn as multidimensional scaling with the parameter metric force. What we could obtain. Here I have three plots. And the first plot is actually a view on three-dimensional data. So you easily recognize the function in the first plot. Which function is that? Sine. This is a sine function, but actually the data was sine function, and then we add the third dimension by adding some random value. And this is view if we look from the third dimension from the above on the three-dimensional set. So if we look from above, we see nice form of the sine. But if we rotate that, then we will see that instead of straight line, we have displaced the points. And after that, we applied principal component analysis and mapped the data into 2 dimensions. And the result was this, denoted here as PCA map. But if we apply multidimensional scaling, then the result is approximately this. So we can see that multidimensional scaling groups the data a little better, so that we can recognize that there is some smooth function from which the data were sampled. Of course, the random noise, which was added as the third dimension, causes that this is not completely smooth. Linear discriminant analysis is another method for dimensionality reduction, which is a little strange. Strange because it is applied for labeled data. So we have actually classification for the data, and our goal is not just to reduce the dimensions, but reduce the dimensions in such a way that the classification will be easy. So even if the dimensionality reduction can reduce the data set nicely, but maybe after the reduction, data which were from different classes will be mapped in some common area, and the classification would be hard after such a dimension reduction. Linear discriminant analysis works in opposite direction, so it tries to map the data to lower dimensions, while to separate the classes as much as possible. The transformation is linear, and I will explain it on the simplest case when we would like to transform the data into one dimension. So we have on the right on the picture, we have two classes denoted by red crosses and blue circles, and we would like to map them to one dimension. One dimension. This can be. We can compute the projection of all the points on some line, and the position on the line will be the one-dimensional projection. So if the first class here has its mean m sub 1 bar, and the mean for the second class is m sub 2 bar, then these means will be mapped to m sub 1, and from the second class it will be mapped to m sub 2. And our goal is to make such transformation that after mapping, the classes will be as separated as possible. What does it mean? So we would like to have the distances between the projections of the means, so M1 and 2, the distance should be big. Whereas the variance in the first class and the variance after projection, so here it is illustrated as sub 1 squared and as sub 2 squared. The variance after projection should be small. If the variances after projections are small and the centers, the means are far from each other, then the separation will be good, and we can easily classify the data. So the criterion when looking for the linear transformation is called Fisher's linear discriminant here, and it's denoted here as a square of difference of the means divided by sum of variances of the classes after the transformation. So in this formula, M1 is the mean, the projection of the mean of the first class. And here are the formulas. I will explain them in detail because in this way, many further formulas will be built. So for distinguishing the classes, we have labels. So the set of observations is set of vectors x sub t. X sub t is one line of the observation matrix, and for each line we have value RT if this is row T, and the value RT is either 1 when the observation belongs to class 1, or 0 if the observation belongs to class 2. So this is the explanation for the for the R for the labels. And if we have this, we can easily formally write a formula for computing the projection of the mean, because the projection, how to perform such projection, we simply take the normal vector of the line. So here, and we multiply the vector W times the original vector to the data point, to the observation, and we obtain one value. So this is a dot product, and this is one value. This will be the coordinate on the line after projecting. So this is the projection of observation x sub t. Using the vector W, and we multiply that by RT. So if we do that for class 1, RT is 1 if the observation belongs to the class. So for RT equal 1, this value will be summed for observations which are from class C2. RT will be 0, so the projection will be not counted. So altogether, we sum the projections here. We sum the projections only for observations from class 1, and we divided by sum of RT. Sum of RT, it's number of 1, so this is actually the number of observations in class 1. Similarly, so this is the this will be the mapping of the mean for the first class. Me sub 1 bar. This is the mean of the original class before transformation, and for the second class. The formula is quite similar, but instead of RT, we use 1 minus RT, because 1 minus RT will be 1 if for observations which are from class 2, and 0 for observations from class 1. And of course, similarly here, when we count the number of observations in class 2, it's just sum of 1 minus RT. And for the variances, it is here, they correspond to variances. So the variances, the values s sub 1 square and s sub 2 square, this is the projection of the observation T minus the projected mean, M1, squared. So this is similar when we compute variance, we compute sum of square differences between the observation and the mean. So the mean is transformed, this M1, and this is the transformed observation, and we compute square of that. And we sum them together. And again, we use the labeling RT. So for the first class, there will be 1 if it belongs to class 1. So we sum the square differences only for observations from class 1. And similarly, when we compute S2 squared, then we take the mapped observation. We subtract the mapped mean of the second class. Take the second square of that and multiply by 1 minus RT. Okay. The square of the differences M1 minus M2 is called between class scatter. So between you would like to separate the classes. And we can express that by simple transforming the formula. So for M1 is the projected mean of the first class. So it can be computed from the mean by W transposed times the mean minus the projected mean of the second class and squared. And here in the formula is in general when we have not only transformation into one dimension, maybe in more dimensions, and not from 2 dimensions, but from arbitrary number of dimensions. So therefore, I rewrite the square into M1 bar minus M2 bar times M1 bar minus M2 bar transposed. Because this can be applied on multidimensional data, and then from the left we multiply by W transposed, and from right by W. The W was when we compute this square, it's always there. So one time we use it for the first in the first half, and the second time in the second half. And what we have here in the middle, we denote as sub B, which is actually a matrix, because M1 bar is a vector in general. For our simple example, this was just one value because we we mapped from 2 dimensions into 1. But in general, it can be in transformation in different number of dimensions. So the original data can have many dimensions. So we take M1 is a vector, column vector. And when we compute M1 bar minus M bar and 2 bar transposed, so we map it into row vector. So column times row vector, the result is a matrix. So this is the between class scatter, and so this was here. And the second part, the sum of the variances, we can rewrite in similar way. So this is for the first variance, the sub 1 squared. So we have the transformed observation minus transformed mean squared times the labeling, or sometimes called indicator. And this can be similarly as above rewritten in the form of W transposed times xt minus the original mean of the first class, xt minus the original mean of the class transposed times W, and RT remains there. So we obtain this form where S sub 1, capital S sub 1, is the corresponding sum, where we sum only the products for which RT is +1. So for the only corresponding to the first class. Analogically, we can do that for the second class, and so the sum S1 squared plus S2 squared can be expressed as similarly as here above, W sub time W transpose time S sub W times W, where S sub W is sum of these two matrices S1 and S2. So I did it intentionally in this way, that because this will be generalized in some following slide. So in general, we obtain that we would like to maximize this formula, and the linear discriminant analysis can be expressed, or how can we solve that? So we would like to find the maximum with respect to W, and we can do that by computing derivatives according to W. I mean, according to each element of W, and the derivative should be 0. And when we solve the equation, we actually obtain that the solution is some constant inverse matrix to SW. SW is here the within class scatter. Times the difference between the means for both classes. Only in case that the classes have a normal distribution, so the probability of observing X for class CI, if it belongs to class CI, is from some normal distributions, then this can then the formula is simpler in that the within class scatter can be replaced by covariance matrix. Actually, it's usually used this form. So it's the covariance matrix because it usually works also in case when the data are not exactly normally distributed. This was just in case we have two classes. We can have more than two classes. The generalization is done on this slide. What I would like you to know, you need not to know all the derivations I have shown to you, but you should know the idea. What should be minimized in order to obtain the solution, and the solution is obtained by some algorithm, and we will not analyze the algorithm, and I will not require you to know such an algorithm. In case for more than two classes, for the labeling, we use such vectors R sub t and superscript I. The superscript is for the class, and it should give 1 if the observation T belongs to class I, and 0 otherwise. And then the transformation is that we would like to transform the original vector X into vector Z by multiplying by some matrix W, capital W, because it's matrix, the matrix of dimensions D times K. D is the original number of dimensions, so the original observations, and K is the new number of dimensions in the after transformation. And the formulas are only a little more general. So the within class scatter S sub W is sum of scatters for each of the classes, and the scatters have almost the same formula. The only difference is here, that instead of two classes, for two classes we have there only R sub t. Now we have R sub t superscript I for the corresponding class. And for between class scatter matrix, we have also similar formula, sum for capital K. Capital K is the number of classes. So be aware of that. We have big K, capital K, this is for number of classes, and small k, lowercase k is the number of dimensions after transformation. And here we have something which is very similar to what we have previously, and the difference is only here, Ni, and Ni is actually the number of observations belonging to class I. It's easy it's easy to interpret this formula. So this part corresponds to variance, and I corresponds to the number of observations. Because if we have several classes, and one class is very small, second class is very big, so it has many observations, then for the importance of the scatter of the variance, this class is more important than this one. So actually, this n sub I is a weighting the contribution of the variance from different classes, and the bigger classes have higher weight. The solution is also by a method that we compute the Fisher discriminant. Actually here, and the solution can be found by eigenvalue decomposition. Don't look at that, or you can look at that I will not require you to know anything about that. So for us, this will be just some procedure. Usually we know that the between class scatter is such a sum of actually k matrices, each for scatter for each of the class, and usually the target value of dimensions is set to capital K minus 1. But in general, it can work for different number of dimensions. Here is an example from scikit-learn library, where the original data sets are the handwritten digits. It's some data set which is built in the library scikit-learn, and after applying linear discriminant projection, we obtain such a mapping where here there are some samples. Different colors corresponds to different digits. If you look at the plot, it's not easy to see. It's not possible to see there are 10 different colors, so the plot is a little misleading. But on the other hand, we can see that the digit zeros are grouped together. Digit 3 are nicely grouped together. Digit 5 are grouped together. So the result is really showing that the differences between the classes is preserved after the transformation. Actually, what we see here is that we map 10 classes. 10 digits, 10 different digits, 10 classes into 2 dimensions. Isomap, there follow 2 or 3 methods, further methods for dimensionality reduction, and for all of them, I present just the idea, not many details. So isomap is a different method. The idea is we have some data in multidimensional space, but maybe the distances between the observations can be computed, let's say, by Euclidean distance. But maybe this distance is not natural in the data, because the data were produced by mapping some lower dimensional space into higher dimensional space. And the lower dimensional space can be, for example, a sheet of paper. Is on this on the left picture, sheet of paper which is bent. The distance, if we compute the distance on the paper, it's different than the Euclidean distance after bending the sheet of paper. So the geodesic distance is based on the on this original geometry. We don't know the original geometry, but what we can do, we can compute for or find for each observation some neighbors. And instead of computing the Euclidean distance, for example, between these two nodes, these two observations, we compute distance based on the neighbor relation. So we compute the shortest distance in this graph. And in this graph, we have edges only for observations which are close to each other. So neighboring observations. So the isomap is trying not to preserve the Euclidean distances, but the geodesic distances. So if two instances R and S, so these are two points, are connected in the graph, and we have in the graph we have edges only for neighboring observations. What are neighboring observations? We take some constant epsilon, and if the distance between these observations is less than epsilon, then we say, okay, these are neighbors and connected. They are connected with edge, and the length of the edge is the distance between the observations, or norm of the distance. So this is the length. And if two nodes are not connected, then the distance between them is computed as the shortest distance in the map, in the graph. This is the geodesic distance. And so we can actually compute such all the distances between all pairs of the observations in the original space based on this geodesic distance. And then we can apply multidimensional scaling to preserve these distances. So in this way, the geodesic distance will be preserved after transformation. And here you can see the results. So on the right-hand side here, this is the result of isomap when this was applied on this banded sheet of paper. So we can see that this was nicely mapped into 2 dimensions. And if we apply that on the digits data set, then we obtain this picture. Both pictures are from scikit-learn. So we can see that the digits are still nicely separated. These are 4s here, and so on. Locally linear embedding is another method how to transform the data and preserve not exactly the distances, but to preserve the relations between distances. And relations between distances, between local distances. So the idea is that if we take an observation, original observation, then the observation says, yes, I have some neighboring is there, much farther is over there, and very close is here. So my distance between these 3 neighbors is that to this I am close to this one, I am farther to this one, and even farther to the 3rd one. After the transformation, I would like to have the same relation between the distances. So if the observation is mapped to some another point, another vector, and this was the closest neighbor, it should be after transformation, it should remain the closest neighbor. And this one was the 2nd closest. After transformation, it should be also the 2nd closest. So it's expressed here. So for each observation xr, we find S a set of closest neighbors. So no, capital S is the number of closest neighbors. So S closest neighbors, and we try to minimize error in the original space. So in the original space, XR minus, and here is some matrix, WRRS. When we multiply the observations X sub S, these are the observations from the neighborhood of the original observation XR. When we multiply them by such a matrix, we should obtain something close to XR. So our goal is to have this norm close to 0. What does it mean? It looks complicated, but actually it says the observation XR should be expressed as the linear combination of the closest neighbors. This is all. So WRS here are just the coefficient used for weighting contribution of the closest neighbors. So if we have a if XR is observation which is it has several neighbors, and XR is in the middle, so the contribution of all these three neighbors will be the same. Of course, this will be different if some of the observations is much closer and are farther, then the contribution will be different. But the goal is that by computing linear combination of the neighbors, I should obtain the value for the observation. So this is in the original space, and then we use that for the so for computing such weights, we can use least square or some other methods. So we require that on the diagonal there should be zeros, and there should be one if it is some of the weights should be 1, and after that we compute the new coordinates, and the new coordinates should have the same property, so that the new coordinate for the observation R should be possible to express as the linear combination of the mapped observations, and the linear combinations with the same weights. So this is the idea, and some illustration. This is in 3D space. In 3D space, we have the observation XR and the neighbors. And WRS are the weights used for computing or enabling to obtain the observation as a linear combination of the neighbors. And after the transformation, we have new vector for the observation R, but the distances to the neighbors should be such that the linear combinations of distances to all these neighbors should the same linear combination should result in the mapped observation R. This is the result for the digits. So theory is nice, but as you can see, And after transforming the digits data set, and the classes are not so well separated, but the method has no information about the labeling. You just look at how they were mapped. But for example, there is also some tools are here. Also here, so it's on this data set. This was not the best choice. In other words, and this is from the scikit-learn. If we have such a banded sheet of paper, this. Do you know the name of this picture in this configuration? It's called Swiss roll. Švajčiarsky rohlík. Zarolované. So this is Swiss roll, and here are observations on the sheet of paper. And after projecting using locally linear embedding, we obtain very nice mapping in 2 dimensions. And it's evident that this mapping preserves the local distances around in neighborhoods of all observations. And still, from the original 3 dimensions, we reduce the dimensionality into 2 dimensions. Okay, this is the end. These are not the only method for obtaining lower for reducing the number of dimensions in observations. Some of the interesting and very usable method is T stochastic neighbor embedding, which sometimes work very well. There are many more methods for reducing the data. What I would like you to know, principles of the method I have shown, just the principles, and I would like you to know principal component analysis in detail. Last week we derived how to compute it, and for rest of the method, just the idea how it works. And of course, I would like you to be able to apply them. We will try such method in the lab, of course. And now let me switch to next part. And next part is on clustering. Is here anybody who has not heard anything about clustering? I suppose not. So I think this should be easy. Maybe sometimes you will see some formulas which could look like complicated, but they are simple, really simple. Look at that; it's simple. So what is the what we have in the part of density estimation? We have parametric, semi-parametric, and non-parametric method. And clustering can be considered also as a type of density estimation. So the goal of the clustering is find where are the groups of the data. So we would like to discover the structure of the data. And the structure, I mean, where are some groups of data? This is the structure. But if we identify where are the groups, so of course, if we approximate the density, so where will be the density highest? Of course, at the part of the space where there are observations. So if we approximate the density, we actually have something which could resemble also clustering, because the density is mostly close to zero in the space, and on some parts of the space density is non-zero. This means there can be some observations. Here are the groups, and if we found places where the density is higher, then we say, oh, okay, this is the places where most probably some data can appear. So there are two methods how to obtain clustering. I mean, two basic methods. It could be also some combinations of the method. The first is grouping. So we start with clusters of size 1, and we join together some close groups in order to obtain bigger groups representing bigger clusters. And the second method is by partitioning that we start with a big set, and we try to split the set in two parts, and then we select some of the parts and split it into smaller parts, and in this way we split the original complete set into groups until we say, okay, let us stop, and we have some groups of data, and these are the clusters. I will speak about these 5 methods. These are not the only method. Take them as example, and as the ideas which are then used in also in some further methods. So let us start with k-means clustering. So k-means clustering is the algorithm which tries to find some k representatives of the data. The representatives here are called reference vectors. Sometimes they are called code words or code book vectors. Why? This will be explained on the next slide. So we would like, as the name is k, we would like to find k such vectors, m sub 1 till m sub k, and each such vector will represent such observation which are closest to the reference vector. So for representing some observation xt, observation is one row in the observation matrix. So the representant will be one of the reference vectors, and which one? That for which the distance between the vector xt and the reference vector m sub j is the minimum. So if the distance is minimal, then we say that this reference vector for which we obtain here minimum, denoted here as mi, is the representative. And the goal for the k-means clustering can be expressed as the minimization of reconstruction error. And here is some formula. I will return to the formula, but let me show you the next slide. Let us suppose we have some observations, and we would like to transfer the observations from the left to the right. For communication, we can use some very limited communication channel, so we can communicate very few different values. And for one vector, we can communicate just one value, one number between 1 and some constant k, for k-means clustering. So what can we do? So we have we obtain some observation, and on the right-hand side, we would like to obtain some vector which is as close as possible to the original observation. But we know that we cannot transfer the vector as a whole. We can transfer just one of k numbers. And what can we do? We can transfer index for the reference vector. And on the so we have the set of reference vectors, which are here. And on the left, we take the observation and look which of these reference vectors is the most similar, so closest to the observation. And the index of the reference vector we will transfer through the channel. And on the right-hand side here on the decoder, we take the index I and we say, okay, we say that the observation was the I's reference vector. We know that this is not exactly what was observed on the left-hand side, but this is an approximation. And what we obtained here, x prime, is some reconstruction of the original observation, and our goal is to minimize the error on the reconstruction. Now we can explain the formula here. So for vector xt, we subtract mi, so this is the ith reference vector, compute square of the norm of this difference, and multiply it by b sub t superscript I. B sub t superscript I is 1 if I is the representative of the observation t. So it's expressed here if the norm of the difference xt minus x minus mi is the minimum of differences between the observation and all among all representative or all reference vectors. So this will be 1 only if mi is the representative for xt. So what we actually for 1, you can see it's a double sum through all observations. So this is t from 1 to capital N, and through all the reference vector I equal 1 to lowercase k. But this square of the norm is accounted, multiplied by 1, only if mi is the representative for the observation. So we actually, if this is 1, let's say the first, M1, the first representative, and in this group we have representative M2, then if we obtain an observation x and we compare the distances to the reference vectors, this one is closer, so we compute the square of the distance between the representative M2 and x, and this will be added. And what is this? This is actually a square of the reconstruction error. Because if instead of x, we transmit the reference vector, we say that the observation was this one. So the difference was the difference between x and the representative. And when we take the square, we have the square distance. And this is the square of the reconstruction error. And the goal here is that if we sum all the reconstruction errors, we would like to minimize that. So our goal is to find such representatives, mi, that the reconstruction error is minimized. So this was the idea. Here is just illustration for the vector b. So observation 1 belong to class 1. So we have 1 for b1, 1, and 0 for the rest observation to belong to the class 3 and so on. So the k-means clustering algorithm works in the following way. We have the input is the data set, so set of observations here, and the number of clusters, k. And we initialize the reference vectors, for example, by randomly generating k vectors, but such initialization is not good. Why? By randomly generating the reference vectors. Here is different method for initialization, and the method is that we randomly select vectors from the set of observations. So if we randomly generate the representative, maybe we generate M1 here and 2 here, they can be very far from the data. So if we randomly pick representative from the data, then the representatives, the reference vectors are closer to the data. So, and then we repeat, for each vector, we compute its representative by computing the B sub t superscript I. So we actually find which of the reference vector is representative for each observation for our metrics. This is the first step. And the second step, if we know that from all these observations have the representative M2, somewhere here, then we say, okay, the representative should be as close as possible to all of them, and we would like to minimize the representation error. So, what will be the best position for the reference vector? In the middle of the set of observations which have this representative. So we compute new value for the reference vectors by computing the means. This is 1 only if observation T was classified as or assigned to the vector M sub I. So we take the value for the vector and multiply by 1 only if it was assigned to as that the representative should be the reference vector I. So we take the sum and we divide it by number of observations for which the MI was selected as the representative. In this way, the position of the reference vector can be changed. And we repeat. So we again compute for each vector its representative. And then for each representative, we take the set of vector which should be represented by the representative, and we compute new value for the representative by taking means, computing mean. And we repeat that until MI converge. So they stop to change, or they change only very little. Here is an illustration. So the means are denoted here by the crosses, and the observations assigned to one of them are marked by circles, and to second just by points. So these two observations were closest to this representative, and all the rest of the observation has the representative this one. After one iteration, we compute mean of these two observations. So the new position of the representative will be in the middle between them. And for the rest here, we also compute a mean. So the second reference vector will be placed in the middle of the group. In the second iteration, we compute the representatives for all the observations, and we can see that here we have only 2 observations which were represented by this representative, this reference vector. But in the second iteration, we have 5 observations represented by this reference vector. And the rest was represented by this one. So we update the values for the reference vectors. So this vector moved a little in this direction, and this vector moved also a little to the left and down here. And again, we assign the compute the representative for each observations. As you can see here, we have more observations for which this vector this reference vector was the representative. So its position is updated and so on. I have a question. Do we have a guarantee that such algorithm will converge? Or it is possible that we will update the representatives in some infinite loop? Say me at least one reason why the algorithm should finally stop. Otherwise, it could happen that in some infinite cycle, we will update the positions for the reference vectors, and we never reach some state where the reference vector will not move. Some simple reason.
How to assign the classes.
Yes, so there is a finite number of assignments for representatives, and this is a very good observation. I agree, but does it guarantee that the algorithm will stop? So if we can cycle with within this assignments for the representatives, then the cycle would be infinite. But we can show that if the algorithm will change the position of the means, then the representation error will decrease. Now we are safe, because if the representation error will decrease, then we know that we are looking for each assignment for representatives, for each observation assigning the representative. There is finite number of different assignments, and we know that each change means we decrease the representation error. At some point, we must arrive at a position where we cannot decrease the representation error anymore, and then the algorithm will stop. So this is just the different formulation for the idea of the algorithm. So assignment, this is where we find the representative. So the reference vectors which represent all the observations, and after that it's refitting step. In refitting step, we move the reference vectors. What is actually denoted here? It's a variant of the algorithm. So. Oh no, let it be. I will not go into such variants. So whenever an assignment is changed, the sum of square distances will decrease. So we are guaranteed that the representation error will decrease. And so this will guarantee that the algorithm will converge. Unfortunately, the result need not to be the best one. What could happen? For example, it is possible that one reference vector will represent such a group where the square distances are quite big. On the other hand, we could have many representatives in some region where there are many observations. So what to do with that? Even if we know that the algorithm converges, if we have some space of possible assignments, then the method is that we actually go in some direction where we decrease the representation error. But if we start with a different initial assignment or with different number of representatives, we can move in different direction the space and in different assignment. So the outcome of the algorithm depends on the initial assignment and initial values for the reference vectors. And we have no guarantee that we found something which have the globally minimal representation error. What to do with that? So we know that the method is not exact and not returning the optimal value. What to do? We must run it many times, and out of the outcome we select one of the results as the clustering. Okay, there is another problem with the data with the method. So final depends on the initialization. So the first method was take k instances from the input. Another method could be compute mean of the data and add k small random vectors to the mean. So we take all the data, compute mean. This will be one point, and then randomly move the point in k different directions, and this will be the initial values for the reference vector. Or compute the first principal component and divide its range into k intervals, for example, equal intervals, and recompute the position in the original space, and this will be the reference vectors. So the idea is, if we know that in the data there is some most important direction, then we place the reference vectors along the direction. These are not the only method how to initialize the data. Another problem is how many how many representatives we need. Let us look at some artificial example. You can see here there were generated 4 clusters, evidently, using some normal distribution, 2-dimensional normal distribution. If we select the number of clusters 2, then of course the best what we can obtain is something that one of the reference vector will represent 2 clusters, 2 of the clusters. For example, if we select 3, then we can obtain that 2 of the reference vectors will represent 2 of the clusters and 1 will represent 2 clusters. If we take k equal 4, we could obtain such nice distribution of the reference vectors, but we are not guaranteed. So we usually must run the algorithm several times, and for example, to compute the reconstruction error and select the result for which the reconstruction error is the smallest. If we take k equal 5, then we could end in such a distribution of the reference vector and similarly for k equals 6. If we compute for each reference vector, we can compute the assignment, which observations were assigned to the vector. And for the group of observations which were assigned to the reference vector, we can compute the reconstruction error. And this is on the diagrams on the right. So if we have k equal 2, then we have 2 big reconstruction errors. One for the set represented by the first reference vector, second for the second reference vector. I should end, I know. For k equal 3, this corresponds to this picture. For this representative, we will have a big representation error, and for the rest, last 2, we have small representation error. For k equal 4, we obtain approximately the same representation error, but probably this value is much lower than this one. So please think of a method how to select the proper number of clusters. I will continue at this point in the next week in the lecture. Thank you for your attention.